Suppose you have a beaker of pure water. So let's say we have 1 dm cubed of pure water, and if it's pure water then the pH will be 7.0 at room temperature. And let's say we had 1 drop okay, 1 drop of bench hydrochloric acid into there. So you might think, well, 1 drop of acid going into a whole beaker full of water like that can't make that much difference. But let's just do a calculation and see how much the pH will change. So 1 drop is about 0.1 cm cubed, which is 10 to the minus 4 dm cubed. Okay, 0.1 divided by 1000 is 10 to the minus 4 dm cubed. If the concentration of the HCl is 1 mole per dm cubed, that means that we have 10 to the minus 4 moles of HCl added. And obviously because it's being added to 1 dm cubed, that means that the final concentration of HCl, which because it's a strong acid is equal to the concentration of H+, will be 10 to the minus 4 moles per dm cubed. And that means that the pH will drop down to 4 with just 1 drop of acid added. And that extreme sensitivity of pH to even quite small amounts of acid being added is a problem potentially, because if you look at, again, biological systems, you find that enzymes, for example, often are very fussy about pH, and they will only work effectively sometimes over quite a narrow range, maybe only 2 pH units in some cases. And so that drop from 7 to 4 could be enough to wipe out the activity of an enzyme. So biology depends on having ways to prevent these potentially catastrophic changes in pH, and biology does that, and in life we do that in various situations too, using a technique called buffering. Okay, so a buffer solution, the definition which you need to be able to trot out is a solution which minimises the change in pH when a small amount of acid or alkali is added. So you've got to be careful about that definition. When you're just kind of, chatting with your friends about buffer solutions, you tend to sort of say things like, oh, well, it keeps the pH constant. But it can't ever completely do that, and that word minimises is important. If you add acid to a buffer solution, the pH will become smaller, but only by a tiny amount, hopefully. Whereas if you didn't have the buffer there, it might, as we saw in the example a minute ago, it might change a lot. But it's minimise rather than prevent. That's important. And small amount is important because buffers have a limited capacity. In the end, you can overwhelm them if you add enough acid. So again, you don't want to give the impression that there's nothing you can do to beat a buffer, because that there is. So definition's important. And the way you make a buffer is that you make a mixture containing a weak acid and its conjugate base. In aqueous solution. Okay, so again you need to know that. So this is what a buffer does, this is what a buffer is. So for example, if we take ethanoic acid as our weak acid, The conjugate base, remember, is what you get when you take one H plus ion away from that. So the conjugate base would be ethanoate. Okay, so a weak acid mixed with added conjugate base gives you a buffer solution. And we can see how it works by thinking about the equilibrium that involves the two of them. So the ionization equilibrium for ethanoic acid goes like this. So you can see if you have your mixture sitting there and you throw in some extra acid, so you drop some HCl into your solution, for example, then this equilibrium is going to shift in response to that change. Because if you've added extra acid, the H plus concentration will rise, and therefore this equilibrium will shift to the left to oppose the change. And that means that provided you've got enough ethanoate there, most of the H plus that's added will react with ethanoate and get converted into ethanoic acid. And therefore the actual change in H plus concentration is very small, because although we've added more, most of it has been mopped up by that back reaction. So we can explain that, and you need to be able to explain that, because that's a very important thing. So if a small amount of H plus is added, the H plus concentration rises, but this equilibrium, and obviously the equilibrium needs to be written down in order to explain this. So don't ever try and explain how buffers work without writing that equilibrium down, because otherwise what we're going to write now would make no sense. But this equilibrium shifts to the left, to oppose this change. If you have trouble with left and right, you can say shift in the backward direction to oppose this change. And that means that most of the added H plus reacts in that backward reaction, and so the H plus concentration does not increase by very much. And that's the buffer having done its work. So the amount that the H plus concentration finally increases by should ideally be a small fraction of what it would have done had this stuff not been there to mop it up. And you can see now why you can't just have the weak acid on its own. You need to have a mixture containing weak acid but spiked with an extra reserve of conjugate base, because ethanoic acid is really very weak. Less than 1% of it, if you just dissolve it in water, is ionized. So that means that there isn't actually very much of this around. So when you add extra acid, if you just had ethanoic acid on its own, the small amount of ethanoic that was there would do its stuff and try and mop up the added acid, but there's so little of it that it couldn't really make much difference. So you need the added conjugate base so that you've got enough of this to mop up lots of added acid. What about if alkali is added? Let's have a think about that. So if a small amount of OH minus is added, so that's not so immediately obvious, because that equation doesn't contain OH minus, so you think, well, that's not going to therefore affect the equilibrium. But of course it is, because if you add OH minus, it will react with the H plus in the mixture. So you say OH minus reacts with H plus, and you should give the equation for that. It's a very simple equation. OH minus plus H plus goes to water. And of course the consequence of that is that the H plus concentration will decrease. Okay, so H plus will tend to decrease because of reacting with the OH minus that you've added. But again, the equilibrium responds to that. Because if H plus decreases, because it's reacted with the OH minus, this equilibrium will simply shift to the right and replace most of the H plus that was lost. Okay, so the equilibrium shifts to the right. So most of the H plus is replaced, and so again the pH doesn't change very much. So you can see the buffer works for both. Because you've got plenty of this in your mixture, it has a good capacity to shift to the right and generate more H plus to oppose the addition of alkali. Because we've got plenty of the conjugate base, it's in a good position to shift to the left to mop up added H plus. So you've got to be able to explain both sides of a buffer's personality, its ability to resist pH change in either direction. What you also need to be able to do are calculations based around buffers. So carrying on with our example of ethanoic acid, we've got this ionization equilibrium. Now we've got a mixture containing ethanoic acid plus some added ethanoate ions, and we've got Ka, which is this. Now when we had a solution that just contained ethanoic acid and no added ethanoate, remember we had to simplify this expression by assuming these two concentrations were the same and getting H plus squared over the total acid concentration as our approximate form of Ka in order to calculate the pH of a solution. It's really, really important to appreciate you can't do that here. Because you've added extra ethanoate, these two concentrations will absolutely not be the same. And therefore, if you attempt to use that same approach to calculate the buffer pH, it's going to give you nonsensical answers. On the other hand, that's fine, because you don't need to. Because in a buffer solution, you add a known amount of ethanoic acid and you add a known amount of ethanoate, so you know what both of these concentrations are independently of each other. And therefore you don't have the same problem that requires you to make the approximations in the first place. So we can just rearrange this expression and get that H plus concentration is equal to Ka times ethanoic acid divided by ethanoate. Okay, so I've just rearranged that, slid this diagonally up there, that diagonally down there, and got this. And that's how you can calculate the pH of a buffer solution. Okay, because if you know what Ka is, and you know what these two concentrations are, you can just plug the numbers in, and that gives you the H plus concentration, and hence the pH. And obviously you can do all sorts of other problems. You could, for example, figure out what ratio of conjugate base to acid you would need in order to get a particular pH. And if you look at the problems, there are lots of examples of various things like this. So let's just look at an example just to make this idea a bit more concrete. So if we're given the information that pKa is 4.80 for ethanoic acid, and let's say we have a mixture that contains 0.5 mole per dm cubed ethanoic acid and 0.2 moles per dm cubed of sodium ethanoate. Because obviously you can't just add a pot full of added conjugate base, you can't just get a pot full of those negative ions, but you can get them in the form of the sodium salt or the potassium salt or whatever. So we could make that mixture, and that would mean that we had 0.5 molar ethanoic acid and 0.2 molar ethanoate, because this is ionic, so it's completely broken up into ions. So we can therefore plug our numbers into there and get that H plus is equal to Ka, so we've got to convert pKa into Ka. So Ka, it's the same operation as converting pH back into H plus. It's 10 to the minus pKa, just like it's 10 to the minus pH. So if we do 10 to the minus 4.8, we get 1.585 times 10 to the minus 5 moles per dm cubed. Okay, so that's our Ka value, so it's going to be that. 1.585 times 10 to the minus 5 times the concentration of acid, which is 0.500, divided by the concentration of conjugate base, which is 0.200, and that comes out to be 3.962 times 10 to the minus 5 moles per dm cubed. Okay, so that's the concentration of H plus that you will have in your buffer solution, and therefore you can work out what the pH will be of that buffer solution as just minus log of that, which is 4.40. Okay, so what that will mean is that if we make up that mixture, it will initially have a pH of 4.40, and if we then add small amounts of acid or alkali to it, it will only slightly drift away from that value because of this shifting equilibrium, which allows it to resist the change. Okay, so that is one way in which you can make up a buffer solution. You can literally get a pot of your weak acid, get a separate pot of the salt of that weak acid, which therefore contains the conjugate base, and mix together the right amounts of each one in your solution in order to get the pH that you want. What's actually as common, or possibly even more common though, is to start with just one of the components. For example, start with the weak acid and add some alkali to it in order to neutralize some of it and turn it into the conjugate base, but not all of it. Okay, so if you have excess of the weak acid and you just partly neutralize it so that some of it remains as weak acid, so you've still got acid in the mixture, but some of it's converted into conjugate base, then you've created a buffer solution. And you quite often get calculations based around that idea. So let's use ethanoic acid again and look at an example of that. So suppose we have 100 cm cubed of 0.5 mole per dm cubed ethanoic acid. Okay, that's our starting point. Now that's not going to be a very good buffer because it hasn't got very much ethanoate, hasn't got very much conjugate base in the solution to mop up added acid. But we can turn it into a buffer by neutralizing some of it. So we're going to add 100 cm cubed of 0.2 moles per dm cubed sodium hydroxide. So the reaction that will happen is just acid plus base goes to salt plus water. So ethanoic acid plus sodium hydroxide creates our conjugate base. So there's our sodium ethanoate with the conjugate base ions there, plus water. Okay, so it's a one-to-one reaction which creates the conjugate base. Now if we work out the moles added, for the ethanoic acid, we've got concentration times volume is 0.500 times 0.1, which is 0.05. And for the sodium hydroxide, again, concentration times volume is 0.200 times 0.1, which is 0.02 moles. Now it's a one-to-one reaction, which means that they'll only react in equal amounts, but we've got more ethanoic acid added, and so fairly obviously this is in excess. And so what we can do is to work out what we've got in the mixture at the end, which will include the excess of this plus the ethanoate that's been formed. So let's do that. So let's first of all get the moles of CH3COO- formed. And you can see that because the sodium hydroxide isn't in excess, all of it is going to react because there's more than enough ethanoic acid to react with it. So if all 0.02 moles of the sodium hydroxide react, we're going to get 0.02 moles of ethanoate formed, because one of those gives you one of those. So we can write that down. Moles of ethanoate formed is equal to the moles of sodium hydroxide added. And you've got to constantly remind yourself that you can only do that because this was the one not in excess, so all of it reacts. So I'll just put that in brackets to remind you that this is the sort of strategy you have to use, is to focus on the thing which isn't in excess. Okay, not in excess, so all of it reacts. Okay, so we know the moles of ethanoate formed is 0.0200. And therefore we can work out the concentration of ethanoate as just moles over volume in dm cubed. And the total volume is 100 cm cubed plus 100 cm cubed, okay, because we mixed 100 cm cubed of each, so it's 200 cm cubed. So that's 0.02 moles divided by 0.2 dm cubed, which is 0.1 moles per dm cubed. Okay, so that's what the concentration of ethanoate will be in our buffer solution. What about the ethanoic acid? So for that, we have to work out the moles of ethanoic acid left over after the reaction. So we had 0.05 moles initially, but 0.02 will have reacted, because again it's a one-to-one reaction. So if 0.02 moles of sodium hydroxide, all of that's reacted, so that will have taken away 0.02 moles of that. So the moles of ethanoic acid left over is 0.05 minus 0.02. Okay, so that's the initial moles minus the moles reacted, which is 0.03 moles left over. So again, we can turn that into a concentration. The moles of ethanoic acid we can turn into the concentration is moles over volume, which is this time 0.03 divided by our 200 cm cubed, which is 0.2 dm cubed, which is 0.150 moles per dm cubed. Okay, so we have a mixture containing the weak acid and its conjugate base, so it's going to be a buffer, and we know the concentration of the conjugate base, and we know the concentration of the weak acid. And so now we're in a position to use the same method we did before to calculate the pH of the buffer. So moving back up here then, we start with our definition of Ka, which is H plus times ethanoate divided by ethanoic acid, and we just rearrange it to solve for H plus, because that's what we need to find the pH. So we get that Ka times ethanoic acid concentration divided by the ethanoate concentration is equal to H plus. Okay, so that's just sliding that term diagonally down there, that term diagonally up there, to give you that expression, and we can plug the numbers in. Ka we had from earlier on, we worked out was 1.585 times 10 to the minus 5 moles per dm cubed. Okay, we got that, worked that out from the pKa that we had earlier on, times the concentration of ethanoic acid, which was 0.150, divided by concentration of ethanoate, which is 0.100, which is 2.378 times 10 to the minus 5 moles per dm cubed. That's the concentration of H+. And so we can finally get the pH is minus log of the H+ concentration, and minus log of that number gives you 4.62. And one thing which is really important to understand about buffer solutions is that they only have a limited pH range over which they're really effective, and that's determined by the Ka, by the pKa of the weak acid that you're working with. So in this case, ethanoic acid has a pKa of 4.8, and as we mentioned earlier on when we were talking about the significance of Ka, that means that at pH 4.8, okay, when the pH is equal to the pKa, it means the concentration of the conjugate base and the acid will be equal. Okay, so the concentration of that is equal to the concentration of that, and that's a sort of ideal buffer because you've got equal amounts of both, so that's maximizing your capacity to resist the pH change when either acid or alkali is added. Now if you play around with that pKa definition, you can soon discover that if you move one pH unit away from that, okay, so at pH 5.8, which is one pH unit higher, so 1 unit above pKa, you find that the concentration of conjugate base is 10 times the concentration of the free acid. And that's getting to the limit of when the concentration of free acid becomes so low that it's not really going to be much use for opposing added alkali. Likewise, at pH 3.80, so 1 unit below the pKa, you find that CH3COO- is just 1/10 of the free acid concentration. And so now we've got the opposite situation where that's kind of approaching the limit of when the concentration of the conjugate base is becoming too low to have very much ability to mop up added acid. So what we're getting around to is the fact that the buffer works best closest to pKa, and the useful range is roughly 1 pH unit either side of pKa. So you can make buffers based on any weak acid you feel like, really, and in general the rule would be that if you know what the pHs you're aiming at, you would choose the weak acid which has a pKa closest to the pH you want, because that's going to come closest to giving you this ideal buffer where you've got equal amounts of acid and conjugate base. Okay, so finally in this little section on buffers, it's time for blood. Blood has got to be buffered because it's got to maintain a pH of around 7.4 to make sure that all the processes that go on in blood are going to happen sort of at an optimal rate. Otherwise, lots of biochemical consequences would follow from that. So buffering of blood is really important. Now the buffer system that's used is this. So your weak acid is H2CO3, which is carbonic acid, which exists in equilibrium with HCO3 minus, hydrogen carbonate ion plus H plus. So it's a traditional buffer system, weak acid in a mixture with its conjugate base. Now carbonic acid itself is formed from carbon dioxide reacting with water, and that's also a reversible reaction. Okay, so the reason that you have carbonic acid in the blood is that you're constantly producing CO2 through respiration, and that's carried around dissolved in the blood, and it reacts reversibly with the water, so some of it gets converted into carbonic acid and some of that in turn ionizes. So how does this work as a buffer? Well, there's a sort of balance between the rate at which CO2 is produced by respiration and the rate at which you breathe it out, which means that the concentration of CO2 in the blood stays reasonably constant, and therefore the concentration of H2CO3 also stays reasonably constant. And the concentration of HCO3 minus is held constant because the kidneys have a feedback mechanism which makes sure that they get rid of just enough of that to keep its concentration essentially constant. And so if those two are kept constant, then you can keep the H plus concentration constant. That's the way the buffering works. So it's the usual story then, that you've got this pH of around 7.4, which you buffer at, and if some kind of process in the body produces extra acid, the H plus concentration rises, but that gets mopped up mainly by the hydrogen carbonate ions in the blood shifting to the left. So you can use that explanation that you've practiced to explain that a process in the blood. Likewise, if something happens in the body which produces extra alkali, that will decrease the H plus concentration initially, but again this can shift to the right to replace it. So you need to know this story, that this is what the buffering system is in the blood, and I guess you should know that this is where H2CO3 comes from. One thing which you certainly don't need to know, but which is quite interesting, is that the pKa for carbonic acid is about 6.3. So you're actually right on the limit, or maybe even slightly beyond the limit of what we've said is the good buffering range for a buffer. So you might think, well, that seems like not very good design on biology's part. But it's quite interesting to see how you get away with it. So if you think about that, 7.4 is just about 1 pH unit above the pKa, and that means that you're going to have lots of this and a relatively low concentration of H2CO3. So that means that if you have extra acid being added, it's fine because there's plenty of HCO3 minus, so the extra H plus ions can easily be mopped up by shifting to the left. The problem comes if alkali is added, if there's a risk of the pH increasing, because in order to oppose that, the decrease in H plus that results from reacting with OH minus, you need plenty of this, and there just isn't plenty of that. So you might think, oh, is that going to be a problem? And the answer to that is, well, no. And one reason for that is this equilibrium. Because remember, although there isn't very much of this in the blood, there's also quite a lot of unreacted CO2. So what will happen is that if this equilibrium shifts to the right to oppose a decrease in H+, concentration of that decreases, but then this equilibrium shifts to the right to compensate for it and gives you more H2CO3. So actually you get away with being right on the limit of what would appear to be the useful buffering range, because biology's clever. And we keep coming back to that. Biology just takes account of things in a much more sophisticated way than you or I could probably manage.